That's what I got as my answer.
Well, let's keep going, and see. So in that case, then G dot del times the vector F is going to be the following. You can take all of this scalar, and multiply it by P, Q, and R. So you're going to have a vector. So you're going to have L Px plus M Py plus N Pz as your first component, then L Qx plus L Qy plus M Qy plus N. I'm confusing myself here. L is N Qz. And your third component is L Rx plus M Ry plus N Rz. Right, so that's how you do that. And similar for F dot del times G. Okay. So really all this is about is you just compute what both sides are and you show they're equal. So you grind your way through all the vector operations, curl, div, that weird thing, this cross product beforehand, and cancel what you can, and it all magically works out. I think what happened was actually.
I didn't actually get the same thing afterwards. Because I didn't work it out all the way yet. So. I'm on the right track though.
Yeah, because when you work out the left side, I actually get 8 terms for each component, because this is a vector equation.
Mm-hmm.
And then you get, on the other side, you get 12 terms, and then you cancel some of them out.
Oh yeah, you say you got 8 and then 12?
Well, but 12 terms on the right side, but you get 2 pairs of terms that cancel out, and then the remaining 8 are equal to the 8 on the left.
Yeah, okay, I did something wrong, because I only got 6 terms in the first half.
Oh, okay.
It's okay, I only did half of it.
Now, so in this case, this formulas that I mentioned earlier in association with problem number 2, 2, apply this time as well, but you have, so this is F dot dr. So in this case, you're going to have integral from 0 to 2 pi, because that's how the curve is parameterized. So then you're going to have f of r of t dot r prime of t dt, where you would have to compute the derivatives of your parametric equations. Cosine t, sine t, sine t. So you could grind it out and do that, or keep in mind that fundamental theorem of line integrals that I mentioned before is f of r of b minus f of r of a. So if you can find, if a function f exists, so you have to check that, is this a conservative vector field? So you can either check it, you're not required to, or you can just try to go ahead and try to find a function that works. Like you said, you saw some patterns that made you wonder. So if you can find a function f, so that fx is this, fy is this, fz is this, then you can just do this, and that is your answer. Otherwise, you're stuck having to do that, which looks kind of unpleasant.
It was. What threw me off was when you get like the cosine of sine of t.
Yeah, I've
And I was like, I don't think that's doable. I typed it into an integrator online just to see what it would give me,
yeah.
and it said it couldn't do it.
Well, I think you know which ways it's going to play out now, don't you? Yeah. Okay. So, So yeah, this is one of those problems that is either possible if you do it the straightforward way, or at least incredibly difficult, or maybe it really is impossible. Or quite nice if you approach it the right way. So whenever you're integrating vector fields over curves, you always want to find out if you're conservative, if you're a gradient, because then you're all set to go.
If you integrate something and it's really difficult, would there be always an end to it, or would it be like pipe where you just keep on integrating forever and ever until you quit?
Well, for some functions, you very
I know there's like
yeah.
like a e or something like that.
E to the minus x squared cannot be integrated. All you can do is write it as a series and integrate term by term, and you'd have to stop at a certain point.
Because you need an X, right?
Yes. Yeah, so without that x there, you're out of luck. Okay.
But I don't think
So,
it's right.
so let's see how 8 played out. You have a surface.
Like, well,
Okay, so the way these are normally done, if now you have parameterization are u and v, and u and v belong to a two-dimensional domain D. So we have a double integral over D, f evaluated at your parameterization, dot product with the normal RU cross RV, du dv. All right, so that's the formula that generally you're going to look at. Okay. Now, in this case we have a paraboloid below the plane z equals 1. Okay. In this case the normal is pointing up, like this. Okay. So you can work on your parameterization. So we have z is equal to what?
I said I might have messed up my parameterization.
All right, let's
Now
find
that
out.
I'm looking at it.
Since we have a paraboloid, it's nice and symmetric with respect to x and y around the origin. If you look down on this from above, because this is z equals 1, what we have here is the, oh, where's that mine?
So I don't think it's mine. I thought I had mine on both.
Oh, yep, it is mine. Okay. All right. This is a unit disk, which suggests you use what to help you parameterize this whole thing?
A circle.
Yes.
Spherical coordinates. Or
Cylindrical.
Cylindrical coordinates, yes.
All right.
That's what I meant.
Is that what you used?
I think so. It's the Z one I'm worried about.
So x is r cosine t, y is r sine t, and then z is just going to be x squared plus y squared, but that will turn out to be r squared.
Yes!
So r runs from 0 to 1, t goes from 0 to 2 pi. Okay, so I said u and v up there, I'm using r and t down here.
I did that right.
Okay, so, all right, so what you can do is, then you can figure out your partial derivatives. So in this case, because of the choice of variables I used, actually, for consistency of everything else I've done in the class before, I'm going to use u and v. Just make it similar to previous examples. So it's u squared. U goes from 0 to 1. V goes from 0 to 2 pi. So then you go ahead and compute RU, RV, and then take your cross products. And so you work all that out, which will go up here. Substitute x, y, and z into so I have x of u v squared, x of u v, y of u v, and then z of u v. All right, so you substitute parameterization in there and work it out.